Okay, we're going to cover Chapter 7 today, and that is energy metabolism. This is one of the more complex chapters, but I'm going to try today to pull out really the key fundamentals that I want you to understand rather than get wrapped up in the little itty-bitty details about metabolism. So I'm going to use the slides at first, and then I'm actually going to turn them off and do some diagrams on the board. So energy metabolism, we use the term metabolism in reference to maybe having a slow metabolism. We can't eat all the calories we want without gaining weight, or maybe someone has a fast metabolism. Energy metabolism essentially refers to how the body gets and uses energy. What did I tell you to think of when you hear the word energy? Calories. Okay? So it's essentially how the body gets and uses the calories. You take in calories from food and then how the body breaks it down and uses it from there. Your liver cells are the most metabolically active. They play one of the key roles in metabolism. And during metabolism, you've got two types of reactions going on. You've got anabolic reactions, or anabolism, and you've got catabolic reactions, or catabolism. Anabolic reactions are when you're building things. You're putting two glucose together to form a disaccharide, okay? Or you're building a new protein in the body. Catabolic reactions are when you're breaking something down. So the digestion is primarily catabolic because you're breaking stuff down into smaller pieces. Catabolic releases energy. If you're going to build something, though, like anabolic, it requires energy. And here are some examples, these are in your book, of different anabolic and catabolic reactions. Like I said, if you were to put two glucose together and store them as glycogen, that would be anabolic because you're building something. Put a glycerol and fatty acid together to create a triglyceride, anabolic. Put two amino acids together or several amino acids together to build a protein, that's anabolic. And then if you were to break these things down, like we do in digestion, these are catabolic, and these release energy that our bodies can use. So ATP is essentially what we know as the form of energy that the body's cells can use. That's what the ultimate goal during digestion is to get things broken down, and then if your body needs to use that energy, it will break it down to ATP. And it can be released anytime you break down glucose, fatty acids, or amino acids. ATP is going to provide energy for all the cells in the body. And you'll see the term coupled reactions. This is so the body has efficiency during the metabolic process, because these reactions are constantly going on. If you broke everything down at the same time, you'd have a huge release of energy. Okay? Or if you built everything at the same time, you'd consume all the energy. So what your body does is couple reactions. So while you're breaking something down and releasing energy, a lot of the times you're simultaneously building something that's using energy. Okay, a few terms. Enzymes, I know we've heard this before because we've gone through the previous chapter. These are facilitators. They're kind of like a push that gives the chemical reaction or gets it going. Coenzymes. These are organic. They're usually a vitamin or a form of a vitamin, and they essentially give the enzyme a push so the enzyme can give the reaction a push to get going. Okay, so I'm going to start with my diagram here, and so I'm going to turn the slides off. And we're going to start where we left off with all the different energy nutrients when we went through the carbohydrate chapter, the protein chapter, the lipid chapter. Okay, so during digestion, carbs are going to be broken down to what? Carbohydrates. What are carbohydrates made out of? Amino acids? They're made of sugars, okay? So you're ultimately breaking those long chains of sugars, which are called starch, down into smaller sugars, and you're trying to get them down into disaccharide and monosaccharides. Your monosaccharides are absorbed into the bloodstream and go to the liver, and glucose is one of your monosaccharides. The other two, fructose and galactose, are converted to glucose. So after you eat and the carbohydrates digested, you ultimately have glucose in the bloodstream. So your carbohydrates from digestion, you're going to have glucose. Okay? Lipids. After digestion, what do you have? What is a triglyceride made out of? Glycerol and fatty acids. Those are the parts, right, that are absorbed into the bloodstream. Proteins. After digestion, what do you have? When you break down protein, what do you get? What are they made out of? Thomas, what are proteins made out of?
Amino acids.
Yeah. So when you break them down, you get single amino acids. Okay? So these are the different things that we now have to work with to possibly get ATP from. Okay? Your body's preferred energy source is glucose. Okay? So let's start with glucose and kind of look at what happens. And I'm going to scoot the camera down a tad. Okay. So you have glucose, and you need to get energy from it. You need to get your muscles need some energy. I'm going to split the glucose in half into something called pyruvate. Okay? This reaction right here, you'll sometimes hear referred to as glycolysis, and this reaction is actually reversible. And that'll be important later. Okay? So to continue with the process, that pyruvate is then broken down to acetyl-CoA. This process is not reversible. So once you have acetyl-CoA, you're stuck with it. Okay? Going through the normal process where you get ATP, you go through the Krebs cycle or the TCA cycle, and we're not going to get into the details of that. And then it would go through the electron transport chain. And then your end result is ATP, water, and carbon dioxide, but with the key thing being ATP. So now your cells have energy they can use. Okay? Okay, this is when your body needs ATP. But let's say you've eaten a lot today and your cells don't really need any ATP right now. Okay? It can take some, if you still got the glucose in pyruvate form, it can convert it back to glucose and store it as glycogen. But if it gets down here to acetyl-CoA and you don't need any more ATP, that extra energy is going to be stored as fat. So acetyl-CoA has two options, ATP or stores fat. Because fat's just the way our body stores energy on it. Yes.
So, how does the body know not to, like, to reverse it? So, does it just automatically reverse, like, or it's like a different?
What do you mean?
Is that what you eat, you know?
Are you talking about reversing it right here?
Yeah.
Well, if you've got pyruvate and your body is sensing that, there's probably some feedback mechanisms that, okay, we don't need any more ATP, and if there's room to store glycogen,
Okay.
then it probably would. Okay. Converting glucose to pyruvate requires no oxygen. Okay? That's referred to as anaerobic. Heard about anaerobic exercise and aerobic exercise? Aerobic uses oxygen. Let me back up. You get pyruvate and you don't have oxygen. You're going to get something called lactate, which is lactic acid, which is what a lot of people blame. Like if you get a side stitch or get a pain in your muscle, you take off running really fast, aren't really breathing, or getting a lot of air in, and you get a pain in your muscle. Build up of lactic acid. Okay? This can give you some quick energy, but your side effect is you get lactate or lactic acid buildup, which causes the pain. Okay? So your body has to recycle that lactate. And with no oxygen right here in the anaerobic form, you aren't getting all the ATP that your body could if you fully broke down that pyruvate with oxygen. Okay? So this is kind of like a quick mechanism. You take off in a sprint really quick. Your body needs immediate energy. That's how you can get it. It's not going to sustain you, though, for 30 minutes. Okay? So, you need sustain, you're going to have oxygen. And it's with oxygen that you can fully break down the pyruvate and get all the ATP that you need. So, with oxygen is referred to as anaerobic. Without oxygen, without oxygen is anaerobic. With oxygen is aerobic. Okay. Let's look at the fatty acids. Let's look at the next thing. Okay, so with lipids, we aren't starting with glucose. What are we starting with? Glycerol and fatty acids. They're going to be handled a little differently. So let's start with the glycerol part. Glycerol is similar to glucose in form, so it can be converted into pyruvate. Okay, the glycerol portion of your lipids. So the glycerol is converted to pyruvate. Assuming you have oxygen, it's then converted to acetyl-CoA. And you have two options. You can break it down for ATP, or if you don't need ATP, you can store it as fat. Okay? Okay, the fatty acids. The fatty acids they go through a process called fatty acid oxidation, and they're converted directly into acetyl-CoA, and then can either be stored as fat or broken down for ATP. Everybody good so far? Okay. amino acids, they first have to be deaminated, meaning you take off that amino group with the nitrogen in it. So once you can do that, some of your amino acids are what we call glucogenic. Can be broken down and converted to glucose. So your glucogenic amino acids can be, after being deaminated, can be converted to glucose, then pyruvate, then acetyl-CoA. When the acetyl-CoA can be stored as fat or broken down for energy. Okay. Other amino acids are what we call ketogenic. And so after they are deaminated, they're going to be converted to acetyl-CoA. So acetyl-CoA, that acetyl-CoA can either be stored as fat or broken down for ATP.
So the fatty acids and the ketogenic, they're kind of the same.
They both enter acetyl-CoA. Okay, so based on this diagram, what we just looked at, what can be stored as fat out of the carbs, lipids, and proteins?
The carbs.
Look at the diagram.
Fatty acids and what?
Carbs, lipids, and proteins.
Oh,
What can be stored as fat?
Well, anything can be stored as fat.
No.
okay, lipids?
If it all goes.
Anything that is converted to acetyl-CoA
Okay.
can be stored as fat.
Which is.
So proteins, carbs, or fats can be stored as fat if you take in too many. Okay?
But it has to be converted down to that particular point, you would say.
Yes. Well, you take in, and that's not that hard to do. You take in excess. So this is what your body's going to do every time you eat. Either you need it or you don't. Okay? Okay. There are certain cells, like your brain cells, that can only use glucose to function. Let's say we haven't been eating many carbs. What could we also get glucose from, based on this diagram?
The lipids. All the proteins. Those glucose.
Okay. Your glucogenic amino acids, and also the glycerol. Because remember, pyruvate is going to be converted to pyruvate. That's reversible. So it can be converted to pyruvate and then glucose. That makes sense? Okay. Now, breaking down carbs for energy is the most efficient. And that's what your body will primarily use as your energy source, and then it'll tap into fat sources. Your body does not like to use amino acids to get energy. It would rather take these amino acids and not even have them enter this breakdown. It would rather take those amino acids to build new proteins in the body. Okay? Any questions so far? Okay, and then so I'm not worried that you know all the different steps in the Krebs cycle, the electron transport chain. What I want you to know is the big picture of all this. Okay, so that's what I'm focused on for this chapter, so that you understand kind of the bigger picture of metabolism. Okay, so I'm going to shift my camera again. Let's take two different scenarios where we might eat. And your book likes to refer to it as feasting and then fasting. But basically, feasting when you're taking in excess energy or calories, and then fasting when you're not taking in enough. Okay? So let's look at feasting and what your body does. Okay, so my let's say it's Thanksgiving, Christmas, I don't know, but you're taking in a lot of energy, a lot of carbs, a lot of protein, a lot of fat. Okay? Your body's going to break it down into glucose, the carbs into glucose, lipids into glycerol and fatty acids, and your proteins into amino acids. Okay? And let's say you've broken down all the ATP that you need. You've stored all the extra glucose as glycogen. What's your body going to do with these now? Yeah. It will store all of these as body fat. Body fat is like your body's energy reserves. Okay, and if you think back to like caveman days, they may have had a huge meal, but then they didn't know when they were going to eat again. It may be several days, it may be a week. Okay, so the body fat is kind of a natural mechanism for survival. You store this extra energy on your body as fat, and then when you need it, you can break it down. Okay. The problem with body fat is that you have unlimited storage capacity. There's only so much glycogen you can store in your body, but fat will just continue to be stored and stored and stored, which is part of the reason why we have a huge obesity and weight problem in the country. Okay, so let's talk about the opposite. Let's talk about fasting. And we're going to talk about, and fasting doesn't mean totally not eating, but it means, okay, what happens 4 hours after a meal, okay, when you hadn't eaten in a while. And then what happens 24 hours later. So let's say you ate breakfast, and it's been 2 to 3 hours now, and your blood sugar's starting to get kind of low, and your cells are starting to need some ATP. Where's your body going to get ATP? Where's it going to get some glucose from to keep you from passing out? Okay. Where's it going to get it first? Where's it going to get the glucose first? Going to take your glycogen stores, where you stored carbohydrates or glucose, and it's going to break that down to get glucose for your blood sugar, for your brain, for those cells that can only use glucose.
So many words, it's kind of like...
And then if this continues, your body will take body fat specifically the fatty acids, and start breaking it down for ATP, for energy. And this is mainly to fuel like the brain and the nervous system, since those can only use glucose as fuel, and this other ATP will fuel all the other body cells. Okay, so this is 2 to 3 hours. What if this fasting continues? Now it's been 24 hours since we've eaten a meal or anything. Where's your body going to get glucose? Where's it going to get ATP?
Probably from the body. Probably from the body fat, because you haven't ate anything, right?
Some body fat, but what happens at this mark is, well, at the 24-hour mark, you've used up all your glycogen. So that's not an option anymore. Remember, you've got to be able to get glucose for your brain and nervous system. Okay? So at this point, your body will actually start taking body protein, like muscle mass, and breaking it down to amino acids. It will deaminate them. And the glucogenic ones, you'll get some glucose from. And that will be used to fuel your brain and nervous system, those cells that can only use glucose. Your ketogenic, you'll get something called ketone bodies. If you've ever heard the term ketosis, a lot of low-carb diets, high-protein diets, kind of, some of them, their goal is for you to be in ketosis, where you limit calories or carbs so much that your body starts breaking down protein some, and you make ketone bodies. And your body breaks down those ketone bodies to get energy for other cells in the body. When your body does that, you're supposedly in a state of ketosis, which is a very acidic state. It's not a healthy, it's not a place your body likes to be. Your body doesn't like breaking down protein to get glucose. It's doing it as a survival mechanism. Okay. Okay, and your body will also continue to break down some body fat, specifically the fatty acids, or the other cells in the body. Okay. So, severe lack of calories or lack of carbohydrate can put you in this state that we see with the fasting at 24 hours. Okay? Basically, you don't have enough calories or you don't have enough carbohydrates, so your body is forced to start breaking down your muscle mass or your body protein for energy. Yeah, you're also breaking down some fat, but you're also breaking down body protein, which you really don't want to do. Okay? Any questions about this so far? Other things that happen during fasting. Okay, think back again to like caveman days. Remember, your body is set up to do this for survival. Okay? So at 2 to 3 hours, your body's not too worried. You know, it thinks, okay, I can survive for a few more hours without food. But then it gets to the 24-hour mark and it's like, okay, I don't know what I'm going to eat again. And it starts kind of going into survival mode and it slows everything down, which is why you hear your metabolism slows if you eat too few calories or you go too long without eating. It's true. Your body starts slowing all your body temperature, your respiration rate, your heart rate, slowing everything down because it's trying to conserve energy. Because at this point, it's like, I don't know what I'm going to eat again. It may be 3 days, it may be a week. So it's trying to conserve as much energy as it can. So your body temperature lowers, your respiration rate lowers, your metabolism, or how many calories you're burning, slows, because your body's trying to protect itself in case it's a long time until you eat again. You also usually have a decrease in appetite, which can help, but this isn't a state that you want to be in, which is why your low-carb diets and your really low-calorie diets are not good long-term solutions for weight loss.
How is that 24 hours affected, correlated to your sleeping?
What do you mean?
Like, is the 24 hours there different from how your body works when it's sleeping?
24 hours, it doesn't matter if you're sleeping or not. It just matters if you haven't had any intake of calories or significant intake of calories for approximately 24 hours. Because at the 24-hour mark, that is essentially when most people have used up all their glycogen. And that's why the shift happens. So you could be sleeping, you could be working out, whatever you're doing, You just hadn't taken in more calories or more energy. Does that make sense?
If you have, as far as the fasting goes, if you have a lot of energy expended through working out, does that 24 hours then shorten to the point of, or as it relates to your body breaking down protein?
If you didn't eat after working out?
No, just if if you were in training for something and you were using up a lot more energy than what would normally be.
Well, usually if you're in training, you're going to be taking in more energy, more calories. And also, the more you train, the more you work out, the more glycogen your body can store. So, which is why it's so important to train, particularly for like things like marathons and triathlons and that kind of thing, because you're training your body, your cardiovascular system, and your muscles, but you're also building up your glycogen reserves because you can store a lot more. So when you do eat, your body's going to store a whole lot more. So usually your total calories are coming up when you're doing some intense training, and then also your ability to store glycogen when you do eat is greater. So you have more glycogen stores. So it's probably not going to differ that much.
Does that make you more susceptible, though, to your body breaking down protein to put you in kind of a danger zone if you're not taking in? Yeah.
Only time you're going to be susceptible is if you're not taking enough calories for the activity that you're doing, or you're not taking enough carbohydrate in. Because if you're taking in adequate calories but really no carbohydrate, that you're essentially, this can happen before 24 hours. Does that make sense?
Yeah.
Okay. Okay, so when you follow a low-carb diet or a low-calorie diet, your metabolism is essentially kind of in this fasting mode, which puts you in a state of ketosis. You're breaking down muscle as well as fat, so it's not a good place to be in. You also need additional water because your body's going to be breaking down those ketone bodies. And remember, when you break down ketone bodies, you get a keto acid and urea. And so your urea is an acid. And so your body is going to want to get rid of that acid. Okay, so you need to take in additional water so that your body can get rid of the urea as part of urine and get it out of your body so your body doesn't get too acidic. Effects of low carbohydrates or being in a state of ketosis. It can cause nausea. It can cause fatigue. Especially if you're really physically active, you may just have kind of no energy. A lot of people like following for a few days because you usually see a big drop on the scale real quick. Okay? That big drop on the scale, though, is primarily water. It may be a little fat, but it's primarily water because carbohydrates in your body, they hold on to water in your digestive tract. This isn't a bad thing. It's not like bloating or something. They hold on to water, and so when you're getting rid of the carbohydrates, you're getting rid of some of the water that's usually here. It can cause constipation, low blood pressure, elevated uric acid, which is a form of urea that you're getting from these broken down ketone bodies. Uric acid is what causes gout. A lot of men, for some reason it's usually men that get gout, where it's really painful, kind of like acidic stones that build up in the joints between toes.
Yeah, I've heard of it.
Yeah. So it can lead to gout. It can cause a bad breath or kind of a foul taste in the mouth. Sometimes if someone's in a state of ketosis, their breath almost smells a little bit alcoholic from the acid, or like they've been drinking. And if you're in a state of ketosis when you're pregnant, it can actually cause an unborn baby to die. Or to be born deceased. So it's not a healthy state that you really want to be in.
Didn't you say people do that for a night though? When their body is in ketone?
Well, any kind of diet that's really low calories. If you're following an 800 calorie diet, that's not enough calories to support your body. So even though you may still be eating, you're not eating enough calories. Okay? Because it probably takes, without even factoring in exercise or activity, probably takes your body about 1,500 calories just to keep your body running, breathing, heart pumping, cells building. Stuff you don't even think about. Okay? So if you are going significantly below that, let's say you're taking in 800, well then your body is lacking 700 calories to just miss. I mean, we aren't even talking about getting dressed and going to school, energy for that. So if you are trying to lose weight, you want to take, and that's called your resting, we'll talk about in the next chapter, your resting metabolic rate. That's how many calories is required to like breathe and heart pumping and that kind of thing. You're going to take that number and then you're going to add an activity factor to it. And then that's how many total calories you need, an approximate amount of how many total calories you need per day. So if you want to lose weight, ideally you should start with that total number of calories each day that you need and then maybe deduct some. But you don't want to go below your resting metabolic rate or that amount to just keep your body running.